So today I'm going to discuss on means as I have means promised in my last lecture that I'm going to discuss on Lyapunov. However, Lyapunov it will be like not only the Lyapunov, rather I would like to start with an means very interesting phenomena of nonlinear system, and then I'll discuss a very small theorem, and then I'll go to the mathematical rigor of Lyapunov. So first, let me just introduce that very interesting phenomena of nonlinear system is known as finite escape time. So what is that finite escape time? If you ask me that, let us compare two systems. One is having an unstable dynamics x dot is equal to x, and another one is having uh, you can say it's a semi-stable dynamics. One sided it is not stable. Both we are considering with x naught is equal to 1. Here also x naught is equal to 1, sorry, minus 1, and here also it is minus 1. So the interesting things here, what you can see or figure out that if you solve this, then you will get, it will give you fine. So with time you will have an exponentially rising curve with starting value at minus 1, but then it will grow exponentially and means continuously grow in negative direction. But the interesting things that you can only claim xt means if xt tends to infinity, then it automatically implies t tends to infinity. Like for any finite t, it is equally difficult for you, although we are no means this is known to us that this solution is not bounded, this is going to be unbounded, but it cannot become infinite within a finite time span for this proof or linear system. However, in case of nonlinear system, if you consider, you will see what that this guy will result xt is equal to 1 upon t minus 1, a very interesting solution, and this solution exists over this closed interval 0 to 1, sorry, semi-closed interval 0 comma 1, and if you make t tends to 1 from 0, as it approaches 1 at t is equal to 1, this becomes unbounded. Isn't it very surprising? Like we have two solutions I am showing you. One is this one, the another one is this one, and it is interesting to note that this one is resulting in this. It is very easy, you can solve it by yourself. I am not going to waste my time on that, but the two things that I am going to highlight here is that for linear system, even if it is an unstable one, then also it takes infinite time to reach the infinite value. It cannot reach the infinite value within a finite time interval. Whereas, on the contrary, if you consider it for nonlinear system, then you can see that for nonlinear system, it becomes unbounded within a very short, or not short, within a finite time interval. Like we can change this interval by means after which, or uh, at the end of which our system will become means if you just replace this by 10, then you will see, you will get here and accordingly it will become this. Well, there is no harm. But what I am trying to say that uh, you are going to get something that is within a finite time, you are going to get an unbounded solution. That is very interesting things. Now, in the light of that, this is known as finite escape time. That is only this type of typical trait you can only find in nonlinear system, not in linear system. So in this regard, let us discuss our one more theorem that will be very helpful. So let f of t comma x is continuous in t and locally Lipschitz in x for all t greater than is equal to t naught, and for all x that belongs to D, where D is a proper subset of Rn. Let W be a compact subset of D such that it contains the equilibrium point. And more precisely, every solution of this equation in the form of x dot is equal to f of t comma x with an initial condition xt naught is equal to x naught lies sorry, I just made a mistake here that x naught is not necessarily be the equilibrium point. That is the initial point. I'm very sorry for my mistake. Please note that this x naught is not necessarily be the part of your means equilibrium point where your rate of state variable cease, but it is the point where your state trajectory is located at your initial time t is equal to 0. So if that is the case, it lies entirely in W, then there exists unique solution that is defined for all t greater than is equal to t naught. So basically what it is trying to say that you are having now a few things you must note here that we are claiming D is a like locally Lipschitz in X. So why do we need two sets? First of all, W and X. Why W is doing here? What is his business here? And even if W is needed, then what D is doing here? Like in that way, we can conceive about means infinite number of subsets and their superset. Like W is a subset and D is a superset. So we can have in that way infinite number of combination of subset and superset. So please note that locally Lipschitz in X. Now you may ask me that in our last lecture you said that if it is locally Lipschitz, then intuitively it is indicating will also become compact. But now you are slightly deviating from what you said in your last lecture, that now you are claiming that X can be Lipschitz in D, but D may not be compact. Now, what is actually what is needed, or why W is needed? Like, this is a very interesting question at this juncture. Try to understand that. This is why you need a teacher, not because I read book and I can share my experience with you. Rather, I can impart not any knowledge based, rather certain questions inside you. And it is my objective to develop or inculcate the habit of questioning. Then only you will be able to understand the subject. So, why W is a compact subset? The way we have stated this problem, it clearly means, although there is no contradiction like D, we are nowhere claiming that W is a proper subset or D is a subset that is not compact. But then also, still the way we have written the statement, you can see here, then it makes a sense that as if D is a larger set in which we are having state means function that is not Lipschitz, but there exists a smaller subset of D, that is precisely our W, that is compact. By virtue of a subset of D, X is also, that function f of t comma x is also Lipschitz with regards to X whenever we will consider the region W. Means basically you will pick up your X from W. That is the whole idea. So why it is so? Like in this context, I would like to give you one small assignment kind of things, although there is no such deadline and such things, that can you construct an example where a set that is not compact but a function on that set is Lipschitz on every point of that set. So what I am giving you in form of an, like you can consider it as an assignment, as a something for brainstorming. You have to construct an example by yourself. You can take help from anywhere, I do not care. But the example should give us a set that is not compact, but still we are having a function that is Lipschitz with respect to the member of that set. So right now, which set I am talking about? That is the set D. Obviously, if a set is not compact, if you take a subset of that that is means if you pick up the element of that subset carefully or select your subset definition carefully, then obviously you can get a compact set even your that superset is not such that way compact. But does it means make sense that even if it is not compact, we can have a Lipschitz? In this regard, I would like to remind you that compactness only not because means only dense is not enough for giving you the compactness. Rather, you need to have something that is set, that is closed and bounded. If you recall the definition of a compact set, it is closed and bounded. And in my last lecture, I have shown that there are few cases or conditions where we cannot represent like compact set. We cannot break it as a union of two disjoint open set, two disjoint closed set, and many other properties I have discussed in my last video. So you can get back there to that video and find your answer. But compact means, and then also the second question that will obviously emerge from this one, that I have also asked in my last video, that why we are so means like eager or so keenly interested in finding out whether the set is open or not. What makes if D is not open? Then what is harm? And if we claim W is compact, then it is not open. So the idea is that why that we are so much is uh, like we have a prejudice for this openness. So why so? Like I think I have already given the answer to you of my first question, but still you just investigate, try to realize, and try to means assimilate the concept by yourself. Anyway, so what is our statement that within the W, then there exists a unique solution that is defined for this. Now, what we are trying to claim that, but before I means try to claim anything, I would like to reiterate the statement of theorem 3 point means that theorem is not you can say it is theorem like of local existence and uniqueness, right? So that existence of uniqueness theorem states that if a function satisfies Lipschitz condition for just let me quickly scribble the theorem of that of local existence and uniqueness. Like for all x y belongs to B, this function is Lipschitz. We wrote it like x a x b. So for all x belongs to Rn, these are actually, we should write it using caps to differentiate them from the scalar, and this is perfectly okay because we are taking the norm, so there is no harm. So if this is the case, oh sorry, we just need to write here the L, that is the very important term here. So anyway, what is that for all xa xp, if we get this condition is being validated by the function f, that is a function of t comma x, then for all b is equal to x belongs to n Rn, such that all t belongs to t0 comma capital T, then there exists some delta greater than 0 such that the state equation, then we again reach the end of the page, but no worry, we can delete this one. We are now quite acquainted with Lipschitz understanding. So if we are acquainted with Lipschitz understanding, we can write for all t 0 comma t, we will get there exists some delta greater than 0 such that the state equation x dot f of t comma x with your xt naught is equal to x naught as a unique solution over the interval t0 comma t0 plus delta. So how we are going to exploit this theorem of uniqueness here to prove this? Like the other way we can prove that if t0 comma t is the maximum interval of existence, we can show you that t is for this case t cannot be means any finite to have an infinite means large solution of our system. Got it? We cannot have, then there exists a unique solution that is defined for all. This unique solution means that solution first of all such that it contains this one, such that it contains, and here means I just didn't write the every let me write, otherwise later on it may create confusion. Every solution of this equation basically lies entirely in W, and then there exists a unique solution that is defined for. So if your W is means by definition W is compact. Compact means you know the bound. Do remember, we cannot write it. It is technically incorrect to write. It cannot be, because nobody can means this is actually the definition of extended real line. We cannot have this plus infinity or minus infinity in our bound. So obviously when you are talking about inclusion of infinity, then it must be a semi-open interval or semi-open set. but W is compact, so W cannot contain infinity. So if that is the case, then the solution itself is finite, and if the solution itself is finite, then obviously if you want the solution to means go out of W, please pay attention to your my word, or means cross the boundary of the set defined by W, then you need T is equal to infinity. For any finite T, it cannot cross your W, because all the solutions, every solution is lying entirely in W. So this is the case that for all finite t, your solution is confined within that term. Anyway, how this theorem turned out to be a useful one, that we will see here. So now with this, let us start. Before I start, I would like to remind you that what is meant by your like autonomous system f dot x dot is equal to f of x. So here you can see that we can define this system as a map from D to Rn, where it takes x, means this D contains all the x, say D, it's like this, it contains all the x, and this f acts on them and they produced x dot. Now this x dot obviously governs the how the next instance, how this element of set x would be, but that is not our intention or means main focus. Rather, our intention is to make sure that you are just trying to visualize this as a map. Now just a minute. Now here, as this system is autonomous, there is no harm in assuming that our origin of the coordinate system is our equilibrium point, that is denoted by x bar. So this x bar is our equilibrium point, and there is no harm that if we define that x bar itself to be located at 0. So we are considering the origin of the coordinate system. Later on we will replace this term coordinate by manifold. That will be more scientific in nature, at what is manifold and why do we need it, that I will be discussing later. Now one thing, that this coordinate system, like x naught is equal to 0, that is our origin of our coordinate system. Now here we can write like, if we find that our state variable means state space, our state space equilibrium point is not located at origin, we can translate the actual equilibrium point, we can define state transformation to shift our actual equilibrium point to shift our means origin of equilibrium, like to define that or to shift our origin of equilibrium in a way where, like, what I can say that this origin or equilibrium become that sorry the equilibrium becomes the origin of that state transformation. So it is like we shift it in mathematical terms. What I can write that I can define a new state variable in this way, where this z dot is equal to x dot is equal to f of x is equal to f of z plus x bar, and we define it as g of z, where g of z is equal to 0. So that is clear. Now that one thing is like the equilibrium point x is equal to 0 is that for the system x dot is equal to fx is stable if for each epsilon greater than 0 there exists a delta, that is delta epsilon greater than 0. This is very interesting that you are fixing up the norm, means this epsilon later will realize this gives a bound in terms of norm. So this actually confine our our what to say that like our ball, or within which the means the function outcome will lie, and then they will predict back what could be the shape of the source, right? So that is very interesting in nature. So here for each delta greater than 0, here what we can write like mod naught is less than delta implies mod xt less than epsilon for all t greater than is equal to 0. That is very interesting things. we will call it unstable. Unstable if it is not stable. That is quite a funny argument. Now, let's see here. In addition, we can say that it is asymptotically stable if it is stable and delta can be chosen such that actually this epsilon delta requirement for stability takes a like a kind of challenge answer form. What is challenge answer? Like to demonstrate that the origin is stable, then you have to conceive certain idea, like certain region there. Like for origin, obviously you have a corresponding mapping of f0, or if f0 is not is equal to 0, then you should do that kind of state transformation, and then in its new transform coordinate system where your origin represent your equilibrium point, for g0 you will get one such means representation there, and then for that will form for any value of epsilon, that is still try to understand that epsilon is like it is in your function range space, it is there in that where your function has mapped itself. So there you formed epsilon, and then a challenger may care to designate that what could be the value of delta, that value of delta, oh God, the value of delta that could yield the confinement of your state trajectories within this epsilon. So naturally speaking, or means if we go by our means like a very naive approach, then generally it comes in our mind that epsilon, that whatever is in the range space norm, that should depend on delta, not the other way around. But why? Why epsilon is not dependent on delta? Rather, we are talking about in terms of epsilon, and then we are trying to figure it back that delta. We are claiming, so basically I am asking you that why epsilon delta statement always framed in this way. So that we must understand and investigate. Now, this is what Lyapunov state, but before we prove it, we need to know, right? So we'll try to know it. What I have decided that instead of means taking that challenger approach and means use so many words and sentences to describe what I feel, to that we can have two function. One is continuous, another one is what happened? Another one is uniformly continuous. So before I go to epsilon delta, let us first understand the difference between continuous and uniformly continuous, and then realize that what would happen if a continuous function is like, what is the genesis, or means how this notion of stability comes in the picture. Because what we said, if you will notice it very clearly, we said that, probably half part I left here, like, this is our system where you are having your we have considered it as an autonomous system. So first of all, it is time or shift invariant. Now think that what type of state space trajectory you can have with respect to time. If you realize that, you will understand that state space trajectories are generated by, like here, if we just reiterate the statement, then you will find that we are considering a system that I guess, like, there I have already written, yeah, this like, uh, even if I do not write, I think I means didn't write it, I think I must have mentioned it, that this F is a locally Lipschitz map. Locally Lipschitz map from R to, means D to Rn, right? So what basically it gives you? F gives you the rate of change of a function. Listen to me very carefully. F gives you the rate of change of function, and that is Lipschitz, means that function rate of change cannot have arbitrary slope, means like arbitrary jerk or arbitrary change in slope. By virtue of the Lipschitz, word Lipschitz implies your function rate of change is bounded by certain constant, and that constant must be a finite constant. So when I try to fill it, when your x dot is Lipschitz, that means x dot, there cannot be any abrupt change in x dot with respect to time. Now when your x dot is a following Lipschitz condition, then how you will get x? By doing an integration. Now think that integration of a function that obeys Lipschitz continuity, can it be such that it would become, or it would give you a certain jerk? Is it possible? Like, can it give you certain jerk? Now, obviously, it cannot. Means it must maintain that, means must be continuous in nature. If your rate of change is Lipschitz, whatever you are getting, that will be continuous in nature. Now think about it, that what basically, that the way we have defined our stability, epsilon, delta, this, that, what basically we are trying to mention here, the notion, what does it mean? Who is the function, who is trying to map whom and where? It is a function, I mentioned once again, that it is basically the state transition itself. Make it very clear, it is no way your rate of change. It is the state transition itself. And state transition is, you can realize the state transition by obtaining time integration of your fx, which is Lipschitz. So that whatever transition you will get, that should be continuous in nature. Now, if the notion of local stability, what it says, that if we find a region where we can, means the region is such, means region is within the neighborhood of our certain point, and we have already discussed that as this is autonomous system, we can always shift its equilibrium point to 0 even if it is not in 0, right? Now, what I was trying to tell you, that if it is continuous, then see the beauty, that if it is continuous, then you are, means you are claiming that in this region, say this is your region, try to understand. First of all, one more thing I would like to mention here, that probably no one or in no book you will find, that nobody states it is actually a function mapping from D to that same region. Means there is nothing like, means generally what, if we are talking about function, some different image comes in our mind, like there is a change in dimension or something. Like just let me give you one example. If I talking about ft comma x, that is today's class I was talking, that it is like it with all the element of D. Here you can have infinite number of elements if you consider that this is a real line T naught, this is T. Infinite number of points can be picked up. Similarly, this D is Rn, like if I am somehow try to draw it, every line you can have independent value of picked up from R. So right, like this one is for first R, second R, third R, like you have Rn. And when suppose if we have two-dimensional case with say then basically what region we are talking about, what D would be. This is for T. D would be somewhere here. With edges, sorry. D will be somewhere here with edges this is our D. I'm giving you a very crude idea, not do not take it so seriously. I'm giving you very crude idea. Now every point will be picked up. Now try to understand this thing, that within this D we are claiming this, within this D this F is Lipschitz. In this D, obviously with respect to x, and also we came to a conclusion that as the system is time invariant, so we can drop this means there is no such trouble. Only here this d is means fx is a function from d to Rn. However, here what is n? In our example, it is R2. Now try to understand that what is actually happening here. You are talking about here you are suppose you are having your initial point, and then by doing something your state trajectory will end up somewhere here. Like if you ask me to draw a picture that describe this whole thing in a two-dimensional plane for an autonomous system, what we are trying to claim that if this is our two-dimensional region, and if we are interested in defining it in terms of Euclidean norm, then this gives us delta. So this delta defines in a region of D. Obviously, delta, the boundary defines, must define a subset either proper or improper of D. Like D can be something greater than delta, means D can be a rectangular region also on which your fx is elliptic, and in that you picked up a region delta, right, where you claim your state trajectory will be, right. Now what is you are talking about, or you are thinking that what would happen, like once you are having something here, it would execute a motion. This line is our state transition line. Typically, it is an integration of your means x dot with your x naught t0 to t, right. Now see what is happening here. This function, it's being continuous. What you will get, it will map every point within this region to another region that may be a bigger circle or smaller circle, in this way that we can have something like what is happening here. these two circles must be concentric, like so some point here, that is x naught, your state trajectory will map it here. Another point, that is due to state transition. And for all possible point lying here, here, you will have their map here. This is your epsilon and this is your delta. Now, the interesting things to note here is that, so now you get certain idea about what epsilon and delta is. Now what I am trying to say, that is more simple thing, that this transition, whatever state transition we have, we can show you here, is taking place through a continuous process. Now we are defining the stability, that if our epsilon is like this whole, means whatever be the points in this circle of cyan color, if my initial point lies inside this cyan color, the final point will lie inside this bottle green circle, right? So this is what all about the notion of stability. Now the question comes that why epsilon depends on delta, not the delta depends on epsilon. The answer is somewhat means simple, because if you want, like, this actually why epsilon depends on delta rather than delta depends on epsilon. Let me just give you one more thing to consider, that what is continuous and uniform continuous function. When you have a function that is where your this delta becomes, now what we are saying, that whatever we are writing here, this delta is totally dependent on epsilon. So once we can remove this dependence on delta, like now it is like there exists some delta E greater than 0, so that x naught less than 0, less than delta implies xt less than epsilon. That is what we are trying to write all over here, right? So, or more precisely, you can write it like xt for all t greater than is equal to 0. Fine, so no harm in that. But what I am trying to say, that is more important to note here, that this one, if this delta depends on your epsilon, then it is only locally stable. But if we find a delta for which it is independent of epsilon, like anywhere you can means your delta can be anything, like the notion of only bounded and uniformly bounded. For only bounded function, you can get some point, means for certain portion you will have certain bound, for some other portion you will have a different bound, but for uniformly bounded function you are having a single bound that satisfies for the entire operating region of that function, like if I am not wrong, what Satyajit asked. Now here this locally stable, when you get some delta that is independent of epsilon, whenever this becomes x naught becomes less than delta, xt will lie in epsilon, then this becomes locally uniformly stable, right? Now if you still have doubt, then I would like to ask you to study two functions by yourself, not by visiting net or other sources. One is fx is equal to root x and another one is f of x is equal to x square. And let me know your view on these two functions, which one is only continuous in epsilon delta sense and which one is uniformly continuous between these two functions. Once you study it by yourself, you will get all the idea clear. In our next lecture, we will discuss about certain theorems. This is the only the definition in or the notion of stability in the sense of lab. Now, next we will discuss how some mathematical tools or theorem to verify our claim. Right?